And we are live with the fourth episode of me trying to learn Rust. So, in the last episode, we basically looked at we finished looking at the most basic construct in Rust. We learned about functions, we learned about for loops, while loops, loops in general. We looked at how to, for example, specify parameters of functions, how to call functions, etc. If statements, and yeah, so basically we covered the most basic stuff, and then we went on to write this very easy and simple and straightforward program that basically asks the user for an operation and two operands, and just prints the result of this operation to start the output. But today we are finally gonna touch something that is the primary reason why I want to learn Rust, which is its how Rust was designed to deal with memory, basically how Rust does memory management. So I basically it would be a good approximation to say that I've only ever worked with garbage collected languages. I think I've already said that my main experience is with Java and Kotlin and maybe JavaScript. All of these languages do have a garbage collector, so you don't really need to think about memory. And I am very curious to see how things are in Rust. So let's see. So understanding ownership. So ownership is Rust's most unique feature. Yes. So basically, this is the main reason why I wanted to learn Rust. As I said, has deep implication for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. We will talk about ownership as well as several related features, borrowing, slices, and how Rust relays data out in memory. So, from what I gather, by seeing people on Twitter commenting about Rust, etc., this is really the core of this language, and it might be that this concept of ownership has some quirks to it. So let's dive in. So what is ownership? So ownership is a set of rules that governs how Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection. Rust uses a third approach. Some other programmer must explicitly allocate them free the memory. So this would be like something like C, while the garbage collected languages are like something like Java, C Sharp, Python, I think. Instead, in Rust, memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the feature of ownership will slow down your program while it's running. So one interesting thing that I can see here is this, that compiler will check. So basically everything will happen at everything about memory happens at compile time, which is also why the feature of ownership will not slow down your program while it's running, which is basically one of the main problems with garbage collector languages. I wouldn't say the problem is that they are slowed down in most cases. Like in most cases, like Java is pretty fast. It's really fast. But the garbage collector sometimes becomes a bit of a problem, especially when you want to do performance analysis. For example, I worked a bit in trying to improve the cold start of some code I was running, and the fact that the garbage collector is not deterministic is kind of like can become quite a pain. And of course, maybe if you really are writing something that is super performance conscientious, is this a word? Like when performance matters like a lot, and maybe it also matters. For example, things like cold start also matters a lot. Maybe yeah, and this is basically system programs, which is what I guess Rust was started for. I mean, I guess it was started for Firefox, if I recall correctly, but I would still say that the performance requirement of a browser are very similar to performance requirement of some system level code. Also because of how the browser landscape works now, looks like now, where we have at least 3 amazing implementation of browsers that are super fast. But anyway, so let's go on with ownership. So ownership is a new concept, so it gets some time to get used to. The more experienced you become with Rust, the rules of ownership system is, you'll find the to naturally develop code that is safe and efficient. Okay, the stack and the heap. Okay, so let me drink some water, and let's go back to university and read back what the stack and heap is. So many programming languages don't require you to think about the stack and the heap very often. For example, you don't really need to think about it in Java. But in system programming languages like Rust, whether a value is on the stack or on the heap affects how the language behaves and why you have to make certain decisions. Part of ownership will be described in relation to the stack and the heap later in this chapter, so it is a brief explanation in preparation. So both stack and heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred as last in, first out. And this is also why it's called a stack, because it works kind of like a ideal stack. I'm not sure if it's actually like implemented as such, but it basically behaves like a stack. Think of a stack of plates. Okay, we know what a stack is. Adding that is called pushing onto the stack, and removing that is called popping off the stack. Okay, all data stored on the stack must have a known fixed size. Data with an unknown size at compile time, or a size that might change, must be stored on the heap instead. So for example, if you have an array of 10 integers, you know that they are 10 integers, that the array size is 10, so you could store it in the stack. If you have an array list of an arbitrary number of integer, for example, because you are reading it as from started input, then of course you cannot put this memory on the stack, because you don't know how big it will be, and so it will be allocated on the heap. So the heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being used, and returns a pointer, which is the address of that location. This process is called allocating on the heap, and sometimes abbreviated to just allocating. And because the pointer of the heap is a known fixed size, you can store the pointer on the stack, but when you want to add the actual data, you must follow the pointer. Okay, think of being okay. And this is also why basically storing things on the heap is much slower. A bit slower. Pushing on the stack is faster than allocating on the heap, because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Allocating on the heap requires more work. You need to find a big enough space to hold the data, and then perform bookkeeping to prepare for the next allocation. Okay, I guess by bookkeeping we mean, for example, we might want to defrag the memory we are using and things like this. Accessing data in the heap is lower than accessing data on the stack, because you have to follow a pointer to get there, yes. Contemporary processors are faster if they jump around less in memory. Continue the analogy, we don't need the analogy again. Okay, by the same token, a processor can do its job better if it works on data that's closer to other data, as in on the stack, rather than further away. Okay, I think there is even a name for this feature of modern processor, but of course I cannot remember it now. But anyway, when your code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and clean up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often, but knowing what the main purpose. Okay, so interestingly, keeping track of what parts of code are using what data on the heap, minimizing amount of duplicate data on the heap, and clean up and use the data on the heap so you don't run out of space are all problems that a garbage collector also solves. I am not sure about the minimizing the amount of duplicate data on the heap, what this exactly means, but definitely what a garbage collector would do is it would keep track of what you are actually using and marking things as removable, as garbage basically, and cleaning them up is literally what a garbage collector does. Again, this goes to show that basically we are learning ownership so that we don't need to use a garbage collector in Rust. So ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Okay, each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So does it mean that, so I am wildly guessing, but does it mean that the string that the read line returned is owned by, for example, the main function? So when the main function basically returns, the compiler will just put some code here that basically are all the free calls that we are not gonna do for things that are located on the heap, for example. Maybe, let's see. Variable scope. So I wonder if we should, let me just not here. Let me just keep a few nodes. Oh, this is a new use me. We don't need to, but we do need to use pageless. So let's call this Rust nodes today. So let's just copy the ownership rules, which let's make it h1. Okay. Now that we are past basic Rust syntax, we won't include all the fn main code examples. So if you're following along, make sure to put the following example inside the main function manually. As a result, our sample will be more concise. Okay, so let's basically, what is this project called? Variables. So let's create a new project. Cargo new. I still have this thing on my hand that basically I cannot use one of my fingers, so typing is actually surprisingly hard. Okay, so let's say ownership. Okay. I do not want. How can I turn this off? Don't show this again. Yes, I want to ignore everything. Oh, actually, I need to leave for a moment. And I am back. So, okay, as a first example of ownership, we look at the scope of some variables. Okay, a scope is the range within a program for which an item is valid. For example, let a equals 1, the scope of a is the main function, for example, or let s equals hello. Okay. Okay, the variable is valid from the point in which it's declared until the end of the current scope. Okay, and of course we can create, so we can create more scopes, like we could do something like this, that b or n equals high. So L is not in scope here, it is in scope here, and it's not in scope here. So basically this value will be dropped as soon as we exit this block, basically. There are two important points here. When S comes into scope, it is valid, it remains valid until it goes out of scope. And at this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Yeah, exactly. Now we'll build on top of this understanding by introducing the string type. Okay, which is basically so a string is basically the first complicated data type that actually needs to potentially be stored on the heap. To illustrate the rules of ownership, we need to a data type that is more complex. Yes. The type previously have a known size, can be stored on the stack, can pop off the stack when their scope is over. Yes. And they can be quickly and trivially copied to make a new independent instance. Yeah, for example, like in Java, usually when you pass an object to a function, it will actually not usually always. It will be always passed as a reference, so it's never copied. But for integers and booleans, and of course every other number type, then the values are copied, so it's passed by copy. And what we are saying here is that basically it doesn't, like for very simple data, it makes no sense, because basically a pointer is just an integer, right? So you might as well copy the integer rather than copying the pointer to an integer. But strings are of course different because they are more complicated. We want to look at data that is stored on the heap and explore how Rust knows how to clean data, and the string is a great example. Okay, we concentrate on the part of string that relates to ownership, and of course this applies to other types as well. We've already seen string literals, like this one, where a string value is our code editor or program. String literals are convenient, but they aren't suitable for every situation, which we might want to use text. For example, if you want to read it from standard input, and string literals are immutable, exactly we maybe not know where this string is coming from. What if we want to take user input and store it? Okay. So for this situation, Rust has a second type of string, which is string with a capital S. So I guess this is what we saw already. Like, is this a string like this? Does this compile? Yes, I also forget again to learn how to do this. Yes, and I also forgot the extension to format. Okay, so it's not a string, it's a pointer to it's a reference. Is this a reference to a string, or is it a pointer to a string? I think it's a reference to a string. Okay. Okay, so basically, and this is not in fact a string. Yes. Okay. So here is where you know that this is a system programming language. When you have two types for string, I mean, I understand that this is like you would never like this would be very wild in some more higher level languages, I would say. But here it is. And this also means that these are immutable, while a string with the capital, like spelled string, can be mutated. Okay, you can create a string from a string literal using the from function, like so. Okay, so basically it will create a new string, and I guess this string is gonna be on the heap, I guess. Double colon operator allows us to use namespace is particular from function under the string type rather than using some sort of name like string from. Okay, so we saw this already, of course. This is also the way you create a new string with a new function. We will see this a bit later. The kind of string can be mutated. Wow, this is also wild coming from Java, that you can actually just append things to strings. Okay, so what's the difference here? Why can string be mutated but literals cannot? Okay, the difference is how these two types deal with memory. Okay, memory and allocation. In the case of a string literal, we know the contents at compile time, so the taxes are coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literals immutability. Okay, unfortunately we cannot put a blob of memory into the binary for each piece. Oh yeah, of course. With a string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to all the contents. This means the memory must be requested from the memory allocator at runtime. So basically you need to call malloc basically at runtime to get some memory that you can use. And then you need to also need a way of returning this memory to the allocator when we are done with our string, so you need to call free basically. So the first part is done, so the allocation part is done by us calling string from. Its implementation requests the memory it needs. This is pretty much universal in programming languages, yes. But then, of course, we are not calling free anywhere because basically, I guess, the compiler will put a free here when the variable goes out of scope. So the allocation part is done by us. However, the second part is different. In languages with a garbage collector, the GC keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. Okay, like in Java, you wouldn't need to think about it because you don't need to call free because the garbage collector will do it for you. And in most languages without a garbage collector, like in C, it's your responsibility. Of course, you need to call free, like in C, for example, manually. And of course, this is super buggy. Like, I mean, it's not buggy per se, but it's very easy to write code that you don't call free. This causes a lot of security bugs and stuff like this. It's so much easy to have like small mistakes that cost a lot in terms of security with this model. And also, it's also very hard to write some reusable code with this model. Like if you want to write, for example, the code we did before, in which you read some string from standard input, for example, or when you write a more complicated framework, it's always very hard to understand. Is the framework freeing the memory for me, or should I free what I'm getting back from the framework and stuff like this? It's just a bit harder to write nice code in this way, especially if you want to make it reusable. So Rust basically avoids you to Rust solve this problem by removing both annoying things of these models. So it removes the garbage collector, which means that the code will be a bit faster and more importantly a bit more predictable. And then it also removes the need to manually code free, which makes the code easier to understand and safer to write ultimately. Rust takes a different path. The memory is automatically returned once the variable that owns it gets out of scope. Exactly. So here it will be freed. Here's a version of our scope example using a string instead of a string literal. Okay. Pretty cool. Of course, all I'm thinking now is this is all very nice until we go to the point in which I need to actually return some stuff, like return some values from a function, for example. So let's say that I have exactly the function we had before. When we read values from the input, then yeah, basically we need a way to tell Rust that actually no, please don't garbage collect. Sorry, this is don't free this value when it goes out of scope because actually I want this value in the calling function. Okay, this is a natural point at which we can return the memory our string needs to the allocator when s goes out of scope. Yes. When a variable goes out of scope, Rust calls a special function for us. The function is called drop, and it's where the author of string can put the code to return the memory. Oh, interesting. Rust calls drop automatically at a closing curly bracket. Note in C++, this pattern of deallocating resources and then at the end of an item lifetime is sometimes called resource acquisition is initialization. Drop function in Rust will be familiar to you if you use RAII patterns. Of course I didn't. I wrote like maybe 100 lines of C++ in total in my life, and I'm not familiar. I mean, I think I heard about this thing, but I've never actually used it. What is interesting is that basically if you write a new type, you need to re-implement drop manually, which I guess it makes sense. But I thought it would be something more like there are a few basic data types. Basically, like I guess string is built with an array, right? Isn't it an array of characters? So I thought that basically Rust could just generate all the code for me to recursively know how to drop everything from a complex type. But we will see. Let's see, drop, function drop, muted self. Okay, so is a required methods from the base trait drop. Okay, I guess this also we need to, I guess trait is kind of like an interface or whatever. Execute the destructor for this type. This method is called implicitly when the value goes out of scope. Okay, so and basically I guess so what it means is basically that I guess when you implement drop, you need to also call drop on everything that you have in your type. We will find out. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's see some of these situations. Ways variables and data interact. Move. Oh, so I heard this verb for C++ as well. So let's see. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in. Okay. So here we are declaring one variable and binding it to the value of 5. And we are doing the same to y, but we are doing so by differencing x. We can probably guess what it's doing. Bind the value 5 to x, then make a copy of the value in x and bind it to y. Okay, yes. We now have x and y, and both have 5 as a value. This is indeed what is happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. But what happens when you do it with a string? So what would happen is, what I would imagine this would happen normally, is that both S1 and S2 are pointing to the same region of the heap that contains actually the hello string. Let's see what actually happens here. So this looks very similar, so we might assume that the way it works would be the same, that is, the second line would make a copy of the value in S1 and bind it to S2. Actually, this is not what I would expect to happen, but yeah, I guess I'm just too much of a Java programmer. Okay, so what actually happens under the cover is that S1 is a pointer. Okay, so S1 is a string, and the string has a pointer to some array exactly that contains the values, and then as a property length, which is the length of the string, and capacity, which is, I guess, it's how big the array is, and of course Ideally, length and capacity have the same value, but for example, what happens if you cut this string? Like if you can mutate it, so let's say you delete the last two digits, then the capacity is 5 because you didn't manually resize the array. So I guess it would still be of length 5, and then length will be 3. Okay, so basically this is the representation of what S1 actually is. A string is made up of 3 parts, shown on the left: a pointer to the memory that holds the content of the string, yes, a length and the capacity. And this group of data is stored on the stack because, of course, we know this at compile time, because we know that a pointer is probably like an I32 or whatever. Same for length and capacity. So basically, S1 is basically just three like numbers. And so of course we know the size and we can store it on this stack, but the array of characters will be on the heap. The length is how much memory in bytes the content of the string is currently using. Oh, interesting. So it's slightly different than what I expected length to be. I thought it was how many characters. I'm not sure if they are actually the same thing, because some character can be wasn't it the case that in UTF-8 you can have characters with a different number of bytes? Well, whatever, I don't think we need to. Basically, we can just take this as it is, so that length is actually how many bytes the content of string is currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator, yes. Okay, the difference doesn't matter in this context, so for now we can just ignore it. So what happens when we assign S1 to S2? So what happens is that, yes, we copy this the stack side of things. So we copy the pointer, the length, and the capacity, but the pointer has the same value, so it still points to the same data on the heap, which is not copied. And this is what we could be thinking that is happening if this was a deep copy, so like we would actually the heap data was copied as well. Of course, then S2 and S1 would be completely independent, and the pointer would have a different value. But this is not what is happening in Rust. Earlier we said that when a variable goes out of scope, Rust automatically calls. Oh, I see what we are going here. So basically, what if S1 and S2 have two different scopes? What happens when S1 goes out of scope? Will drop things for S2 as well? Let's see. So we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the memory for that variable. But figure blah blah shows both data pointers pointing to the same location. This is a problem. When S2 and S1 got out of scope, they will both try to free the same memory. Okay, so this is a different kind of problem, but still the same thing. So basically, yeah, like we are trying to drop in twice the same heap space. This is known as a double free error, and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. Okay. To ensure memory safety, after the line S2 equals S1, Rust consider S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Oh, interesting. So basically, if you assign to another variable S1 will be considered not valid anymore, and you cannot use it anymore. So basically, the compiler can just remove this code and just put this here and move. Oh, you get an error like this because Rust prevents you from using the invalidated reference. Move occurs because S1 has type string, which does not implement the copy trait. I guess this means that you could implement this copy interface and then assigning a variable to another variable would mean actually copy also the heap value. Okay, so we move this value, allocated on the heap to this variable here, value borrowed after move. Okay, this error is in the macro. Okay, so very interesting. So if you heard the terms shallow copy and deep copy while working with other languages, yes, we did. So basically what Rust does is a shallow copy, but since Rust does also invalidates the first variable, instead of calling it a shallow copy, this is known as a move. Okay, so in this example we would say that S1 was moved into S2. So what actually happens is shown in figure 4. Okay, so basically this is grayed out because it's not valid anymore and the values are moved. Okay, this solves the problem, of course, because when S1 goes out of scope, since it was invalidated, drop will not be called on S1. Also, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. Any automatic copy can be assumed to be inexpensive in terms of runtime performance. Okay, so this is also cool because, so I think in the 100 lines of C++ that I wrote in my life, I always struggled a bit to understand when do I need to, when should I copy this, when should I pass a reference or whatever, is this expensive enough, is it not expensive enough, and whatever. So in Rust we say that the Rust will just never create a deep copy of anything that is on the heap. So basically if an automatic copy is happening, we can be assumed to be inexpensive, which is nice. Less things to think about. Okay, if we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone, which I guess will do a deep copy. Okay, is an example, and now basically we do need to drop both S1 and S2 because they point to different heap memory. Okay. When you see a call to clone, you know that some arbitrary code is being executed and that code might be expensive. Okay, stack only data, copy. Okay, so what about stack only data like numbers? There's another wrinkle we haven't talked about yet. This code uses using integer, part of which is shown blah blah, works and is valid. But this code seems to contradict what we just learned. We don't have to call clone, but X is still valid and wasn't moved into Y. And the reason is because numbers, they are always on the stack. The reason is that types such as integers that have known sizes compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we would want to prevent X from being valid after we create the variables Y. In other words, there's no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. It's also probably the most common occurrence when you want actually this behavior, when you have two variables that have this pointing, they have the same value. It may be some, I don't know, some index you want to start from or whatever. So this is actually working as, this is basically as in Java, where everything is passed by reference except for the the primary types. Those are actually copied because copying is so inexpensive that we can just do that. Also, as we already saw somewhere, Rust has a special annotation called, it's an annotation called the copy trait. I guess trait is like a type or an interface or whatever, that we can place on types that are stored on the stack as integers are. If a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. So maybe sometimes you have some very trivial data, like for example a range. A range is just two integers, so let's just not it would make sense to allow this copy behavior because it would be very inexpensive to do. Rust won't us annotate a tab with copy if the type of any of its part has implemented a drop trait, which means basically that anything that it contains can be is allocated to the heap, I guess. If the type needs something special to happen when the value goes out of scope and we add the copy annotation, we'll get a compile time error. Okay, blah blah. We will have other available traits in Appendix X, in Appendix C to see about this. This is a bit, so I would say that it's a bit sad when you need to, I mean, I don't know. I need to check what does Rust mean by annotation. If this was the Java like meaning of the word annotation, I would like this a bit less, but let's see when we get there. So what types implement the copy trait? You can check the documentation, blah blah. For example, all the integer types, okay, we already know about this. Tuples, if they only contain types that also implement copy. Okay, makes sense. Yeah, as I said, this is basically the range example that I had, right? So you have two integers. Why wouldn't you want to just copy them? It wouldn't make sense to actually move them. Oh, okay. So here comes the part that I am more interested about the ownership and functions. So the mechanic of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy. Oh, okay, just as assignment does. Okay, so basically S now owns this memory, then takes ownership that now S is invalid, basically, right? S value moves into the function, so is no longer valid here. Okay, so this S is no longer valid. X comes into scope, and now it's okay. Now it's copied, so X is still valid, I guess. So it's okay to still use exactly. And how do we declare a string? Okay, some string comes into scope, and then it's dropped here. Okay, and the memory is freed. Okay. Nothing special happens because it implements copy. Okay, so this is also great because this automatically prevents one of the worst patterns that I see in Java that I hate so much. It's when you want to like initialize an object, and instead of having like a builder or whatever, you just call some methods that like you do user equals some user, and then you do something like add name of user and blah, and then you have 5 of these functions, and then you return the user. So this is the most ugliest code ever, and I'm really glad that basically the compiler will prevent you to do that in Rust, which is great. Okay, so far it's pretty straightforward. Basically, when you call a function and you pass an argument to it, the variable you use as an argument is basically gone from the rest of the function that is calling. Like you cannot use it anymore because it was moved inside, let's say, the body of the function that you're calling, and its value will be dropped when the function has executed. Okay, and Rust will actually enforce this at compile time. This is really cool. Okay, for example, yeah, we can try to break this. For example, let's write a function called greetings, which accepts the name of someone, which is a string, and it will just call print line hello name. So, and we have our name, which name should we say? KZ, nice. No, okay. Let's just say KZ. Greeting name. You can guess which YouTubers I am currently watching lately. So greeting and then greeting once more. Let's see. Will this compile? Actually, this may compile because Kezi is a string literal. So let's see if this works. Oh, actually, okay, this does not compile for another reason. So let's to string, yeah. And actually, yeah, this I think will work, but for some other reason that. So this will work, yeah, exactly. But this will work because I am creating new values here. I am basically copying stuff here. I think. So that's why these are actually different values, and so that it's not unexpected that this would work. But this will not work. Exactly, value used after move, which is actually the example that they were making here, just using from. So this could be also written as from. Let's see. Yep, this does not work. And this will work indeed. Okay, makes sense. Return values and scope. Okay. Return values can also transfer ownership. Let's see. So give ownership. So this function returns a string, which means that we'll move its return value into the function that calls it. Okay. So here we are allocating a new string, and we are returning it. And so now the ownership of it will be in the calling function main here specifically. Okay, takes and gives back. Okay, this function takes a string and returns one. Okay, this is actually much more straightforward than I thought. I mean, this seems pretty simple so far. Takes a string and returns one. I guess I will regret saying that this is much more straightforward than I thought. I am sure that when you actually write some real code, this thing will be a bit more complicated. Maybe we will see some cool examples here. We will see. The ownership, so, and basically this, okay, a string comes into scope, a string is returned and moves out of the calling function. Okay, nice. So actually you can still like write the ugly pattern, you just need to return also the value, which is basically a builder, so I think I would be fine with that. So the ownership of a variable follows the same pattern every time. Assigning a variable to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be dropped, unless ownership of the data has been moved to another variable. Okay, I have a question. And I don't want to read later things. But let's say that we want to have another function which is called, for example, decorate, and which will take a string and return a string. And it will basically name append, I think. Let's see. Rust string. It's a prepend maybe. Append as push string appends a given slice onto the end of string. Copies. Okay, let's just use push string. So, and we say we append. What could we say? Hello. Okay, so we have our string, our name. We have our decorated, which is called decorate name. So, and this will compile, I think. It does not. Okay, why not? Expected stream found tuple. Oh, this mutates. It doesn't. So I still need to. Okay. So I would have expected push string to return a string, but I guess that would mean you would need to copy it. So that's why this API is a bit ugly. So we need to explicitly kind of cannot borrow as mutable. So yes, actually. So first of all, this we need to say that this will be mutated. First error, I think, right? Consider this to be mutable name, okay. And then we need to also say that this is mutable. And now we only get warnings because we are not using the remove this mute. Okay. Oh, because, okay, so I think we don't need the mutable here, because what actually other information you will get, because we still know that decorate will own this memory anyway, and so it doesn't really matter if we if this is mutable or not, because this can do whatever he wants with it, I guess. I guess this is why we don't need mute, I guess. Okay, so basically what I wanted to say, and then we can we can just print line it once, just to see this without decorated, without the ugly warnings. Okay. Of course, we cannot just print a string. We need to wrap it in a string literal. Okay, so yeah, so this works. But what happens if I remove this? So now decorate will move name to its color, so here, but there is no variable to hold this value here, so there is no value to call drop on. So does Rust just basically knows that I guess yes, I guess that basically this will behave as if you implicitly created a variable, and Rust will just know, the compiler can figure this out. Let's see. Yeah, exactly. Okay, this still works. Makes sense. Makes sense. Okay, taking ownership and returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also need to be passed back if we want to use it again. I would say that it's probably a good idea most of the time, actually. But okay, so basically we are saying that why do I need to return this? Because I am mutated name. So I may want to say, let me just keep using name. I guess we want a way of saying that decorate should not actually own this value, and main should still do it. And this means that basically when decorate goes out of scope, when the body of decorate, when the scope of its body finishes, like basically here, we don't want name to be dropped. So without explicitly returning it, basically. So how do we do that? Pass it back in addition to any data resulting from the body of the function that we want to return as well. Okay. Okay, you can. Why is it relevant? Oh, I see. Okay. So, okay. For example, okay. This is an example to show an even more like clear example of why we want this actually. So basically, let's say you want a function that basically can tell you if how long hello is, right? So it needs to return a number, a size, unsigned size. But of course, you still want to use the string that you use, right? You need to use hello. And so if you always call this, if you only change the ownership of S1, then what happens is that you need to return two values, the values that you passed, and then the value you actually calculated, which is very, very tedious. Okay, and so that's what borrowing is. So basically, we want that to decorate instead of owning name, we want decorate to borrow name, so that the callee is still the one that owns the variable. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Okay, so let me make a guess. So what we do is we add this ampersand here, and then we don't need to return anything. And of course it's not, okay, so we need to do this to say, actually pass the reference of it. We need this to be a mutable reference. Okay, you know what, let's just read what the book says. Let me go back. Okay, references and borrowing. Okay, we already saw this issue, we already know. That is, okay, here's how you would define and use a calculate length function that has a reference to an object. Okay, so yes, exactly. So this is similar to what I wrote, right? You say that calculate length actually accepts a reference to S, and which is, why didn't this work? Isn't this correct? Remove this mute. Cannot borrow name as mutable as it is behind an ampersand reference. Let's see. I know I should just read the book, you know. I absolutely know. But sometimes, you know, when you read the error from the compiler, you may help understand better what the book is trying to tell you. Expected a reference of a string, found a string. Of course, this is, we want to pass a reference. Consider changing this to be a mutable reference, ampersand mute string. But this is what I had before, so this should be a mutable string. Because of course we are mutating it, so this makes a lot of sense. Name is a reference, so the data it refers to cannot be borrowed as mutable. Oh, okay. So you cannot borrow something and change it. So basically this is actually working as intended. Like, I guess you cannot, like, this is very different. Like, let's say we wanted to, doesn't string has length size? Length? You know, a long time ago, I did a small app for mobile operating system that nobody remembers, nobody used, and that did mostly failed. And my app was featured in a blog post. And of course, I was very young and I didn't know English that much. And the app was converting like meters into, I don't know, inches or whatever you guys are using in the US. And I misspelled length. I wrote it like this, which I consistently do it like from time to time, even today. And this was my such a high moment for me. Like I was in an actual blog. Actually, people were actually looking at something I did, and there was this very embarrassing spelling error in all the screenshot it had. So I still think about this from time to time. So we want to know the length of this string. Maybe it was actually here. Yeah, okay. Yeah, of course. Basically, I am just redoing what this example says. So I might just as well just copy everything. Yeah, of course this works because we are not mutating the input string. Okay, notice, so let's read about this this code. So first, notice that all the tuple code in the variable declaration and the function return. Okay, yes, we are not using the pattern anymore. Like, we are not returning s and the size. We are just returning the size. But here we are still using s1 even after we passed it to calculate length, meaning that the value was not moved from s1 to calculate length, but it was borrowed by calculate length and still belongs to s1, I guess. Is this the right terminology? Okay, second note that we pass ampersand s1. Is it called ampersand, this thing? I would say and. We will pass m s1 into calculate length, and not in its definition we take, and in its definition we take an end string, so a reference to a string, rather than a string. These ampersands represents references, and they allow you to refer to some value without taking ownership of it. Okay, so we have s, which is here, which is calculate length, which is a reference, so it in the reference basically has a pointer, which points to s1, which of course also has a pointer to the actual array that contains the string. Okay, makes sense. Note the opposite of references by using ampersand is deferencing, which is accomplished with the deference operator star. We'll see some uses of the deference operator in chapter 8, and then we discuss blah blah in chapter 15. So why do I need to, like, isn't this okay? I guess we will know later why we may want to, why we might need this. So let's take a closer look at the function call here. So again, we create we allocate a new string, we call calculate length passing a reference to s1, which means that after this line we can still use s1. The reference s1 syntax lets us create a reference that refers to the value of s1 but does not own it. Okay, and of course this means that this value will not be dropped. Like here, s is still like the value that s references to is still valid. It is not dropped. It will be dropped here. Okay. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter s is a reference. Okay. The scope in which the variable s is valid is the same as any function parameter scope, but of course it's not dropped. Basically, the value pointed to it by the reference is not dropped when s goes out of scope. Okay. We call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back, and you don't own it. Okay, yeah, okay, so we call this borrowing. So the value of s, the memory that from will allocate is owned by s1. Is it owned by s1? How do we say this? Is it owned by s1? Is it owned by the scope of s1? What is the correct terminology? I'm not sure yet. But then basically calculate length is borrowing the value referenced by s1. Okay, so what happens if we try to modify something we are borrowing? This will not compile, as we already saw. Consider changing this to be a mutable reference. This is exactly what we saw before. This is the example we tried. We are not allowed to modify something we have a reference to. Consider, oh, but wait, consider changing this to be a mutable. Okay, I think I got the, like, let's say, I think I got the syntax wrong. We have a decorate and we have a string, which is and mute string is so, and then I will append, no, push, we will push hello, and we want to, we have a name, let's say Mario, we want to decorate name, and then we want to print it. and of course we want to pass a reference to name. So let's see what I expect this to. So I expect now the compiler to complain that name is not mutable. Yeah, wait, first it complains again that you need to wrap this. And then types differ immutability, arguments of this function are incorrect. Expected mutable reference, found the reference of a string. Okay, so we need to call this, we need to mark this as mutable. Types differ immutability. And do I need to do this as well? Of course, this is unused now. And it does work. Okay, so you can actually mutate a borrowed value. You just need to use this other syntax. Okay, interesting. Yeah, this was the other chapter, mutable references. Yeah, we already saw exactly this example, how it works. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. Makes sense, because of course you would need to track how they are mutated otherwise. This code that attempts to create two mutable references to us will fail, and the compiler will tell you that because this is called a mutable borrow. Okay. So when you create a mutable reference, you are actually doing a mutable borrow, and you can only do one mutable borrow. Okay. The first mutable borrow is in R1 and must last until it's used in the print line, but between the creation of that mutable reference and its usage, we try to create another mutable reference. Okay, the restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. The benefit of having this restriction is that Rust can prevent data races at compile time. Oh yes, because actually this is perfect for multithreading, right? I mean, you can only mutate this thing in one thread, right? How does memory borrowing and ownership work in a multi-threaded environment? We will find out. Anyway, so basically this seems safer. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. Okay, but wait, wouldn't this be still a problem even if you had one mutation? Like you can still read something weird from at least one of the pointers is being used to write to the data. Wait, is it I can't create the same? Yeah, but how this limitation work? Like if I can still have two references to name and one of them is a mutable reference, then I can still occur in this I can still occur in this, right? I can, at least one of the pointers is being used to write to the data, yes. If I have two references, at least one, and one is mutable, at least one can be used to write data, right? Rust prevents this problem by refusing to compile code with data races. So I guess, yeah, I am not sure, I'm not really sure about this section. I guess Rust must do something a bit more, right, to prevent this. Like you don't get this for free just by saying you cannot create multiple mutable references, I think. It could be I am missing something obvious, but yeah. As always, you can use curly brackets to create new scope, allowing for multiple mutable references, just not simultaneous ones. Okay. Similar rule for combining mutable and immutable references, code results in an error. Oh, okay. So, okay, now I see. So you can only have one mutable borrow across all borrows. Like you can, how can I, like, basically you can either have one mutable borrow or an immutable borrows. Okay, then this also makes, then I understand. Okay. Yeah, okay. We also cannot have a mutable reference while we have an immutable one to the same value. Okay, then it makes a lot of sense. Users of an immutable reference don't expect the value to suddenly change out from under them, yes. However, multiple immutable references are allowed because of course we can guarantee that nothing changes to this value, so you can just read it from whatever thread and it will be always safe. Okay. For instance, this code will compile because the last uses of the mutable reference, the print line occurs before the... Okay, so Rust is also very smart and understands that R1 and R2 are never used after print line. Because a reference scope starts from where it is introduced and continues through the last time that the reference is used. Okay, cool. So R1 goes out and R2 both go out of scope in this line. And then you can create a mutable reference and it will be safe. Okay. The scopes of the mutable references are R1 and R2 and after the print line where they are last used, which is before the mutable blah blah. Okay. The ability of the compiler to tell that a reference is no longer be used at the point before the end of the scope is called non-lexical lifetimes. NLL for short, and you can read more about it in the edition guide. What's the edition guide? Oh, so this was a feature in Rust 1.31. Wow. Okay. So at the beginning, this was not possible, but in a version like 4 years ago, it became possible. So they added this ability to the language. Cool. Blah blah. Dangling references. So in languages with pointers, it's easy to erroneously create a dangling pointer, a pointer to the reference allocation in memory that may have been given to someone else by freeing some memory while preserving a pointer. Okay. In Rust, you can never do this because the compiler will guarantee that the references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Let's try to create, okay, so here what we are trying to do is we are saying, let's return a reference to a string from this function. So we create a string and we return a reference to it. But what do we expect to happen is that we return a reference to this string s, but then s here goes out of scope. And so s will be dropped. So how can this work? And the error is that the compiler will tell you expected named lifecycle. What is this? But anyway, it will fail basically. The function return type contains a borrowed value, but there is no value to be borrowed. Yes, exactly, because this will go out of scope. So what do? We give it a static lifetime with again this very weird syntax. Okay, to a feature we haven't covered yet, lifetimes. We discussed lifetime in detail in chapter 10, but if you disregard the part about lifetimes, the method does contain the key to why this is a problem, of course, because you are returning a borrowed value, but there is no value to be borrowed anymore. Yes. Okay. Yes, of course. So we create a new string. We return a reference to the string s. But then s is dropped, and so its memory goes away, and so the reference to s is now pointing to some random memory stuff, whatever. So what do we want to do instead is moving s to the caller, right? Because s is can say dangle, blah blah. The solution here is to return the string directly. Ownership is moved out and nothing is deallocated. Okay. So, to recap, at any given time you can have either one mutable reference or any number of immutable references. A reference must always be valid. Next, we look at a different kind of reference slices. So, slice, I think, is something like an array that can grow. The slice type. Slice is that you reference a continuous sequence of elements in a collection rather than the whole collection. Okay, so it's about, yeah. So I think for today we are done. This was the coolest episode, I would say, so far. It's this ownership and borrowing concept is very, very cool. I think I may need to write a bit of Rust to actually see when this will become annoying. So far, I cannot really, like, I think from what I heard on Twitter and whatever, it seems that sometimes, also just from warnings in this book, like a few times it was mentioned that people will struggle with this, and you may write code that would look totally okay in some of the languages, but not in Rust. And I think we will need to write some actual code. I wonder how much more chapters are necessary to actually start writing something. So we have structs and structured related data, enums and pattern matching, managing growing project with packages, crates and modules. Okay, this I think we can just skip entirely. But maybe common collections we can also, maybe we can skip, like we could just Google it. Header handling, I think this we may want to take a look. Generic types, traits and lifetimes also we will want to take a look. Writing automated tests, I also think we can skip. For the scope of, I don't think it's very interesting to see on stream how to write tests. And your project, building a command line program. Okay, this we definitely want to do. This we will definitely do. Iterator enclosures. Oh, this I would also very much like to take a look. Smart pointers. This also sounds interesting. So fearless concurrency also cool. Okay, so there are a lot more chapters that I would be interested in this book. And then I think I may need to prepare some, like maybe we should do one episode in which we just write a very simple program. Maybe I could even retry to re-implement the only program I've ever written in Rust. It was very simple and I didn't need to understand that much about borrowing and stuff, but maybe now I could write it better. It was a command line argument, a command line program to basically generate a string with an emoji for the battery level. And then I would use it in my Tmax configuration to see the battery level in the bottom right. I think that would be cool, maybe to do as a first thing after we maybe after we go past the using struct to structure data, to structure related data. But we will see. So far, I have to say I'm really enjoying Rust. It would be cool to have the opportunity to actually use it at work, for example. I don't think it's gonna happen soon, but you never know. Yeah, that's pretty much it. Thank you if you followed, if the video was interesting, and hopefully it's also motivating you to learn Rust or learn some other random language. I don't want to say that Rust is a random language. I say that I am learning it despite the fact that it's not really related to my job or anything, but just for the pleasure of learning something new. Okay, enough with my random mumblings. Is it a word, mumblings? Sometimes I'm not sure if I am actually speaking correct English, but whatever. Okay,